space. So let's start with bagging. Bagging is such a joyfully simple idea. It's like this. You have a training set, you learn a decision tree on it, right? This is the traditional thing. The idea in bagging is just the following. I'm going to generate random variations of my training set, right? In a way that we'll describe shortly, but I generate, let's say, 50 different variants of my training set. And then I learn a decision tree on each one of them, or whatever, but let's say decision tree. Right? These methods are usually very popular with decision tree learning for good reasons that we'll talk about next week. So I learned 50 decision trees. Okay? So now I have 50 decision trees, and along comes a test example. What would you do?
Vote.
Vote. Yeah, exactly. Remember, it's always a good answer to a lot of machine learning questions is vote. Whoever has the most votes from decision trees is the winning class. Yeah.
How do you change your training set? Every time you generate a tree from it. I mean, because if it's the same set,
of course,
you get the same tree every time.
So let's get to that question. You do this by generating what are called bootstrap replicates of the training set. In fact, this is an idea that came from statisticians, and what they did was extend to learning classifiers, something that had been around for some time and been heavily studied for doing things like estimating variances and means and the kinds of stuff that statisticians worry about. So what do? You create bootstrap replicates. Bootstrap replicates because what you're doing is you're pulling yourself up by your own bootstraps. What you would like to have, right, is 50 different training sets, but you don't. So what you have is one, and then you fake 50 different training sets. The way you do that is by sampling with replacement. It's a very simple idea. Let's suppose that my training sets consisted of 1,000 examples, right? I'm just going to generate another data set of 1,000 examples in the following way. I'm going to randomly pick an example from the training set and put it in the new set. And then I'm going to do the same thing again, but with replacement. If I did it without replacement, I would just wind up with the same set again. When I did with replacement, what happens is that there's a certain chance that one example would get chosen twice.
Oh.
And a few examples will even get chosen 3 times. And there's an exponential decrease in
there will be some samples that aren't chosen at all.
Exactly, and there's some examples that aren't chosen at all. So what happens at the end of the day is that you have a training set that's of the same size as the original one, and the important thing is that the statistics are actually still the same, unless you look at very fine-grained statistics, but the usual statistics are still the same. So this is sort of like where the statistician's knowledge was very useful, is that you've created a data set that statistically looks just like the real ones, right? It looks just like taking a new, sample from the original process. Of course, if you're looking at things like, well, how many times do you get duplicates? Well, now this is going to give the wrong answer because you're going to get more duplicates than before. But in terms of things like averages and variances and whatnot, you actually get still pretty much the same thing. Okay? And the procedure is very simple, right? Just sample with replacement. In fact, sampling with replacement in terms of implementation is easier than sampling without replacement, right? Basically, every time you just repeat the same thing of like randomly pick one of 1,000 and keep going, okay? And then what happens is that you have 50 different training sets, and 50 is not a random number. When you do bagging with 10, it improves things a lot. 20 improves them a bit less. 50 very little, and 100 is seldom worth the trouble. Okay, so 50 is usually a good number to go for. But if you're short of time, 20 is also okay. 10, you're already losing something substantial, right? You learn 50 decision trees, and then you just vote them. Very, very simple idea, right?
So you take an item from the test set, send it to all the trees, and whichever is the most common decision wins?
Yep.
Okay.
So here's this thing graphically, right? So I have my original sample. I generate my so-called bootstrap replicas, 1 to n. I apply my base learner to each one. We often, in model ensembles, we often call the learner that we're wrapping the ensemble over the base learner. There could be more than one. In this case, there's just one. It's the decision tree learner. Okay? But it could be something else, right? So I run it through the base learner, and of course, each one of those runs produces a different model, right? And then what happens when I have a test example is that, I just send it to the ballot box. Each of the models votes, you are spam, you are not spam, and then the majority class wins. Now the beauty of this is that after you've spent, in the old days, a long time implementing decision trees, these days you might just use an existing suite, but after spending a long time playing with your decision tree to, make it, do as well as possible, you do this to it, and your accuracy could easily go up by 5%, maybe 10. And once you're into that part of the curve where you've gotten to 78%, but it's really hard to get to 80, suddenly being able to get 83 is amazing, right? If you're a credit scoring company, 5% better accuracy is a big deal. If you're Google, 5% better accuracy on people clicking on the ads is a big deal, and you can get it with basically a couple hours worth of effort. So very worth having. Of course, it costs more cycles, but these days we have a lot of cycles. Now, what's the key thing that is essential for this to be useful? All right, let me put it this way. This will work for decision tree. Do you think it will work for naive Bayes? What if my Bayes learner was naive Bayes? What would happen? I generate bootstrap replicas of my training set, right? And then I'm going to count how often the class occurs and how often each attribute occurs with each class, right? And what do you think is going to, these models are going to look like? Are they going to look different or are they going to look similar? In the cases of naive Bayes, they're going to look very similar, right? Because bootstrap learners preserve those low order statistics. They are bootstrap replicates, right? That's what that's why they were designed, right? So this will not work with naive Bayes because you just get 50 times about the same classifier. The thing that's kind of perverse about this is that it will work very well for decision trees because of something that is actually a disadvantage of decision trees, or at least superficially a disadvantage, which is that, and I don't know if you've observed this, but you can certainly try it with your learner and something like the e-commerce data. What happens with the decision tree learners are very unstable, as are multi-layer perceptrons, for example. Meaning that I change a few percent of the data in your training set at random, and you could learn a completely different decision tree. And this at first is very disturbing, because it means that you can't really trust what the decision tree looks like. Sure, it's accurate, but don't get hung up on all the details of what's in that tree. The upper levels, they're probably meaningful, but once you get down to the fine details, you run it again, you get something completely different. So decision trees are unstable. And unfortunately, instability and power go together, right? Naive Bayes is not unstable because it's also kind of dumb, right? So, smart algorithms, maybe like smart people, are more likely to hallucinate, right? You could be a genius or you could be a madman. So, bagging is very easy, but it only works on learners that have this property of instability. The amazing thing about bagging and some of these other methods is that after all that we've worried about pruning, once you put an ensemble over things, exactly how much pruning you do doesn't really matter anymore. You probably still want to do some pruning, but the fine points of where you prune, you're probably better off under pruning. Why is that? Why would you want to under prune when you're going to run an ensemble? Right? Let me ask you the question this way. Should you run the decision tree learner with the same settings whether or not you're doing bagging?
No.
No, because?
Get very similar models again if you do a lot of pruning.
Exactly. If you under prune, right, the bagging will average out the overfitting. That's the beauty of it. Bagging is a great overfitting control technique, right? One of them was like this, the other one was like that, right? Bagging, the majority is going to win. Only where the decision trees agree are they going to prevail. So bagging is very simple, but it's very powerful. When we talk about learning theory next week, we will see a more fundamental explanation of why bagging and other ensembles work in terms of two quantities called bias and variance, which are very popular among machine learners. But for the moment, we will just stay with this intuitive understanding. Questions about bagging?
Just to confirm, each of the Bayes learners is exactly the same, right?
In bagging, each of the Bayes learners is exactly the same, but it could also be different learners. Right? And again, we will see later some algorithms where the learners are different. In general, the theme in model ensembles is that you need some way to generate variation, right? The way you generate variation could be by varying the training set, it could be by varying the learner, it could be by varying the parameters, it could be, for example, in the case of backprop, by varying your initial weights. Okay? So there are many different legitimate ways of generating variation. For example, here's an interesting little point. There's actually a way to make bagging work with naive Bayes. You know how? Clearly, randomly selecting instances isn't going to help me, but is there something else that I can do that will generate a lot of variation?
And noise, change the
training set.
Adding noise actually again doesn't work because it will tend to wash out because I'm computing these very low dimensional statistics, right? Just how often each word occurs, right? But there's something with
Add missing values.
well, sure. I mean, there's a bunch of things that you can do, but let's suppose for a moment that there are no missing values, right?
Find naive ways with other types of learning trees or learning models, like mix up with learning trees or something and bag them together.
Yeah, again, you could do that too. It's not the answer that I'm looking for, though.
Use different features maybe? Or
Yes, exactly. What you can do is instead of doing, bootstrapping over the instances, you do bootstrapping over the features. Because with respect to those naive Bayes is unstable. You take out some of these high information features and now it's going to have to rely on others. And of course, in low-dimensional problems, there's not going to be much to do. But for example, let's say you're doing text classification, which naive Bayes is very good for, right? You have 10,000 dimensions, right? So there you have plenty of room to do, bootstrapping over the features. So, and you can think of your own, just as people did, right? You can think of your own way to generate variations of the algorithm or the data or whatever, and see if that works. In fact, there's a lot of papers in the machine learning literature about this, and combining these different methods and decision trees with naive Bayes at the leaves, with bagging over them and whatnot, right? So.